This work presents and demonstrates learning controller gains on bipedal walking robots via user preferences. The goal of this work is to enable the use of complex controllers on bipedal robots by alleviating the gain tuning process through preference-based learning. This process is demonstrated on both the 3D robot Cassie and the planar biped Amber. In both cases, the robot went from stumbling to walking in a matter of hours. The benefit of preference-based learning is that it is a structured method towards identifying non-intuitive parameters without needing to numerically define a reward or objective function. In the case of bipedal locomotion, this is important since there are often performance trade-offs that are challenging to numerically weight. The general process of preference-based learning applied to tuning control parameters is as follows. In each iteration, the robot is given a set of gains selected by the algorithm. After viewing the resulting behavior, the operator gives a preference of worse or better as compared to the previously sampled gains. The operator also gives an ordinal label of bad, okay, or good. The algorithm then updates its belief of the underlying utility function and provides a new set of gains to execute on the robot. This process is repeated until the operator is satisfied with the experimental performance. On Amber, a total of 50 iterations were completed, resulting in stable walking using a CLF-QP Plus controller. On the left is the performance near the beginning of the experiment, and on the right is the stable walking achieved using the gains identified as optimal. Notice the oscillations and poor tracking performance at the beginning of the trials compared to the stable walking achieved at the end. The process was then extended towards learning gains of an IDCLF-QP Plus controller on the 3D biped Cassie, and was conducted for a total of 100 iterations. Testing near the beginning of the experiment is shown on the left, and the behavior associated with the optimal gains is shown on the right. Again, preference-based learning was successfully able to navigate the landscape of controller gains and turn torque chatter and poor tracking performance at the start of the trials into stable, robust locomotion by the end. To highlight the framework's ease of use, the experiment on Cassie was repeated with a naive user providing feedback, which once again yielded successful locomotion. Overall, all experiments identified controller gains that resulted in stable and robust experimental locomotion. The success of the final CLF-QP-based controller is further illustrated by the ability of the robot to tightly track operator commands, as well as the robot's ability to resist external perturbations. Moreover, locomotion was achieved without in-depth robot-specific knowledge or months of gain tuning. Lastly, we would like to thank our sponsors for supporting this work.